In episode 46, titled Reinforce Cryptography Essentials with Actionable Scenarios, we lean into short, realistic situations that move cryptography from whiteboard theory to everyday judgment. The goal is practical fluency, seeing the moving parts, choosing sound defaults, and knowing what evidence proves you did the right thing. Rather than sweeping generalities, each scene focuses on one decision, one risk, and one outcome you can justify to a reviewer or incident board. By the end, you should hear the rhythm of good cryptographic hygiene in your head, the way keys, algorithms, and controls line up so that confidentiality, integrity, and availability are supported without drama or guesswork. Picture a team securing design documents stored in a shared project space. The requirement is file at rest protection that holds up even if the storage system is copied or the host is lost. The team chooses Advanced Encryption Standard, AES, in Galois/counter mode, GCM, with a unique data encryption key per file and an authenticated metadata header that pins the algorithm, version, and nonce. Keys are created and wrapped by a hardware security module, HSM, or Managed Key Management Service, KMS, with access controlled by short-lived roles rather than long-lived users. Recovery tests confirm that decrypt operations require the right role plus the right environment. And audit logs show who unwrapped which key and when, turning encryption from a checkbox into a verifiable control. Now consider an administrator portal where credentials and commands traverse the network. The team selects Transport Layer Security, TLS 1.3, with mutual authentication, so both sides prove identity. Server certificates chain to an approved certificate authority, CA, while client certificates are minted by the organization's public key infrastructure, PKI, and scoped to the admin app. Cipher suites prefer AES GCM or ChaCha20 Poly 1305, and session tickets are short-lived to limit replay windows. Health checks verify certificate revocation status via Online Certificate Status Protocol, OCSP, or stapling, and monitoring watches handshake errors for early warning of drift. The outcome is not just a lock icon, but a documented, repeatable identity proof on every connection. Password storage demands a different rhythm. The application never stores clear text. It stores verifiers produced by a slow key derivation function, KDF, such as Argon2ide or script, with a unique per-account salt and parameters tuned to exhaust adversary hardware. A high-entropy system, Pepper, lives in an HSM, so a database snapshot alone cannot power offline guesses. On login, the system derives once, compares in constant time, and caps attempts with exponential backoff and risk-based controls. Evidence lives in parameter versioning, migration logs that show past hashes upgraded to safer settings, and a playbook for rotating peppers without forcing mass resets. The point is simple: degrade an attacker's guessing speed to the point that stolen databases become noise rather than catastrophe. Integrity for an application programming interface, API, often hinges on message authenticity, not secrecy. Here, the team issues each client a scope-limited secret and requires a hash-based message authentication code, HMAC, over the canonical request line, headers, and body. Timestamps and nonces block replay. Scope limits enforce least privilege, and rotation is routine rather than reactive. If a secret leaks, the blast radius is bounded to the scopes assigned, and server-side detections flag signature failures and skewed clocks. The artifacts that matter are the key issuance records, rotation cadence reports, and sampled request transcripts that demonstrate signatures verify end-to-end. When auditors ask, "How do you know this call is genuine?" the system can answer in detail. Software supply chains live or die by authenticity. In this scenario, the build system signs release artifacts with an asymmetric key whose private half is guarded in an HSM and whose public half is widely distributed for verification. Every artifact carries a detached signature and a manifest of expected checksums. Deployments verify the signature before a single byte touches production. If a build server is rebuilt, the process reattests provenance and refuses unsigned packages. Reviewers want proof that signing keys rotate on a schedule, that old keys are retired with a signed statement, and that verification is enforced, not optional, in the deploy pipeline. The result is a chain of custody a third party can trace without trusting any single machine. Hybrid encryption shines when you need performance and selective sharing. The sender generates a random data encryption key for AES-GCM and encrypts the content once, then wraps that small key under the recipient's public key using RSA OAEP or an elliptic curve scheme. To share with multiple recipients, the content stays put. Only the wrapped keys multiply. The recipient unwraps the data key, verifies the authentication tag, and reads with confidence. Logs show which public keys were used, when, and under which policies, while failures clearly separate cannot decrypt from integrity failed, avoiding ambiguous errors. The pattern scales because the expensive asymmetric step stays small and the symmetric step stays fast. Certificates eventually expire, and when they do at the wrong moment, it feels like an outage you chose. In our scene, a public endpoint fails because the certificate lapsed overnight. Recovery begins with reverting to a known good configuration, renewing via Automated Certificate Management Environment, ACME, and validating ownership cleanly. The fix does not stop at renewal. Monitors are set to alert weeks in advance, auto-renew is configured with dry run tests, and the acceptance path checks the full chain, including intermediates and revocation responders. Post-incident notes document time to detect, time to recover, and what changed to prevent recurrence. The lesson is that cryptography is operational. You schedule it, test it, and track it like any other reliability dependency. Sometimes the finding is a weak cipher lurking in a default. Here, the team discovers DDES and SHA-1 accepted by a legacy endpoint serving paying customers. Rather than a risky Big Bang cutover, they stage a migration by first adding strong options, measuring client adoption, and then disabling weak suites behind feature flags during off-peak windows. Canary nodes enforce the new set, telemetry tracks failures, and customer support has clear messaging for the stragglers. The final step is making the desired state declarative in configuration management so the weakness does not return. When challenged, the team can show dates, traffic graphs, and change approvals that prove a controlled, low-risk evolution to modern cryptography. Key compromise is the scenario everyone dreads and few rehearse. In this case, a signing key used for internal tokens is suspected stolen. The response begins with rotation to a fresh key pair, revocation and publishing of a signed retirement statement, and an emergency reduction of token lifetimes across services. Dependent systems read a new trusted key set through configuration management. Verification code accepts only current keys plus a short overlap for in-flight tokens. Affected artifacts are re-signed, long-lived credentials are reissued, and logs are combed to map where the old key was trusted. The record shows what was rotated, where, and when, and includes a gap analysis for places the key should never have been. Recovery is not just regaining function, it is proving the old trust path is truly closed. Backups deserve the same discipline as production because attackers love them even more. The team adopts envelope encryption. Each backup chunk receives a unique data key. Those data keys are wrapped by a key encryption key kept in a separate KMS account with restricted administrators. Restore workflows require dual control, and cross-account logging prevents the same person who extracted a backup from also unwrapping keys are noticed. Periodic fire drills prove you can restore within the recovery time objective without bypassing controls just this once. The evidence trail includes key policies, rotation schedules, successful restore reports, and approvals that show separation of duties was real in practice, not just on paper. Privacy requests introduce nuance. A data subject demands tighter access on their records stored in a shared analytics table. Rather than decrypting the entire data set, the team designed ahead with per record or per tenant data keys and a rewrapping path. The record's data key is unwrapped in a controlled service, rewrapped under a new policy or public key, and the surrounding data set remains untouched. Audit logs tie the request ticket to the exact key identifiers and timestamps involved, giving regulators a crisp story with minimal data exposure. This is selective re-encryption as an operational capability, not a theoretical exercise, and it pays for itself the first time a large table does not need to move. Before we close, it helps to connect each scene to first principles and the proof that satisfies scrutiny. Confidentiality was enforced by strong, well-implemented primitives and carefully handled keys. Integrity was anchored in signatures, authenticated modes, and deterministic verification. Availability relied on automation, rotation, and staged change. Across them all, the artifacts recur. Key policies, rotation logs, certificate chains, build attestations, deployment gate outcomes, and access approvals with dates and names. A reviewer does not want adjectives, they want artifacts and timelines. When your cryptography stories align with that expectation, even tense moments become defensible decisions rather than folklore. Taken together, these scenarios suggest a house style for encryption work. Make the safe way the easy way. Make identity explicit at boundaries, and make evidence a byproduct of normal operations. The tools are familiar, but the craft lies in scoping secrets, constraining trust, and rehearsing the rare events so they are routine on the worst day. When your team thinks in these patterns, you spend less time arguing algorithms and more time proving outcomes. That is how cryptography supports the mission without becoming the mission. Use this momentum to capture a concise playbook that mirrors what you just heard. Draft short response patterns for file encryption, transport protection, password verification, message integrity, code signing, hybrid exchange, certificate renewal, cipher deprecation, compromise rotation, backup restores, and selective re-encryption. For each, define the trigger, the decision points, the default algorithms and parameters, and the evidence you expect to see after success. Keep it short but concrete enough that someone under pressure can act without improvisation. The result is a living operational map that turns cryptography from scattered knowledge into a dependable part of how your organization works every day. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.